Welcome back to the shop floor. I'm thrilled you're here. Look, today in this explainer, we're going to deconstruct the raw, fundamental physics of how vehicles actually turn, and more importantly, the mechanical systems we engineer to make it happen without tearing the drivetrain apart. Consider this an engineering masterclass on the mechanics of cornering and differentials.
To kick things off, let's look at this absolutely brilliant quote from a vintage 1937 instructional film from Chevrolet. It perfectly, and I mean perfectly, isolates our core kinematic constraint. The man on the outside has to ride a lot farther and a lot faster. The outside wheels must spin faster than the wheels on the inside. It's just a simple, undeniable fact of geometry, right? But managing that physical reality, that is the absolute foundation of everything we're diving into today.
So just as a quick baseline for us, a differential is simply a gear arrangement allowing two output shafts to turn at different speeds, all while sharing torque equally from a single input. Now you already know the basics, but it's wild to think this was first patented in its modern automotive form by Louis Renault way back in 1899. He took earlier concepts and packaged these bevel gears to solve that nasty, destructive problem of wheel slip and axle binding on corners. It was a total game changer.
Okay, here's our design brief for this session. We're going to hit the kinematics of cornering, break down the open bevel differential, look at traction limits and failures, explore welded and planetary solutions, dig into the helical limited slip, and finally, wrap up with materials.
Section 1. The kinematics of cornering. Let's get into the math. Let's start with the hard numbers that govern every single differential out on the road. Look at this constraint equation right here. Omega L plus omega R equals 2 times omega C. In plain English, the left and right wheel speeds have to average out to the carrier speed. It's the absolute law our drivetrain must obey. There's no cheating it. If your carrier is spinning at 100 RPM and you take a really tight turn that slows the inside wheel down to 90 RPM, the planetary geometry dictates that the outside wheel must speed up to exactly 110 RPM. The speeds diverge, but they always average out to the input.
All right, moving to Section 2, the open bevel differential.
Let's do a quick teardown to see how the hardware actually pulls off this mathematical balancing act. The input torque comes in from the pinion gear, driving that massive ring gear, which in turn spins the carrier. Inside that spinning housing, you've got your spider gears riding on a hardened crosspin. And those mesh perfectly with the side gears going out to your half shafts. When you're driving dead straight, the spider gears don't rotate on their pin at all. The whole unit just spins as one solid locked block. But the second you enter a turn, those spider gears start spinning on their cross pin. They maintain a strict 50-50 torque split while letting the side gears rotate at those independent speeds we just talked about. And as an engineer, the trick is maintaining a super strict backlash of exactly 0.10 to 0.20 millimeters between the side and spider gears. If you don't, you're going to get some serious thermal binding.
Which brings us to Section 3, traction limits and failures.
Now, any senior engineer will tell you that you learn the absolute most from how a system fails out in the real world. So let me pose this to you. What happens to that perfect 50-50 torque split when traction on one wheel drops to practically zero? Well, this is the Achilles heel of an open differential, because it matches torque evenly. If you hit a patch of ice and your slipping wheel can only handle, say, 50 pound-feet of torque before giving out, the wheel on dry asphalt with all the grip in the world gets exactly 50 pound-feet. It completely limits the total output. You're left stranded, and the engine's power is just entirely wasted spinning that slipping tire.
And honestly, that leads to a catastrophic failure mode. Imagine you're stuck in deep snow, and you just floor the throttle out of frustration, hoping to break free. That extreme free spinning causes the spider gears to rotate on the crosspin at ludicrous speeds. It literally slings the differential oil completely away from the mesh points. You get severe metal-on-metal friction, massive heat buildup, and eventually the crosspin will heat score and literally weld itself to the spider gears. Boom! Drivetrain destroyed. Oh, and as a side note, if your backlash tolerances drift even slightly past 0.25 millimeters, you'll start hearing this awful 30 to 50 mile per hour whine, which means you're going to find chipped gear teeth sitting in your diff fluid soon enough.
Section 4, welded and planetary solutions.
So to get around these traction limits, we have to engineer workarounds and, of course, heavily weigh the trade-offs. The open def gives us great cornering but dies on ice. A really cheap, budget-oriented alternative is a welded spool. Literally just taking a welder to the spider gears so the two axles are physically locked together. This guarantees 100% of the engine's torque goes to the axle as a single unit. It's awesome for drag racing or throwing a budget drift car sideways, but the downside? Daily drivability goes straight out the window.
it totally prevents the wheels from turning at different speeds, so the car just violently skips, hops, and scrubs tires through corners, putting immense, terrible torsional strain on the axles.
If we want to actually engineer a sophisticated solution, we look at the planetary gear alternative. This coaxial design is beautiful because it eliminates the offset shafts completely. Since multiple planet gears are meshing all at once, they share the physical load simultaneously. This gives us unbelievable torque density and shock resistance. You can hit high single-stage reduction ratios, anywhere from 3-to-1 up to 10-to-1, and crucially, you can engineer asymmetric torque splits. Think of 40-60 rear bias for a performance all-wheel drive system done entirely through pure gear geometry. The catch, though, is that it costs us big time in manufacturing complexity. The nested structures require incredibly tight, unforgiving machining tolerances.
Section 5, the helical limited slip.
Now, for a dedicated high-performance track application, say a Formula Student race car, we iterate toward a mechanical device that biases torque effectively, but without the sudden, jerky locking of a welded spool. Looking at this exploded CAD view of a custom helical design, check out how the helical pinion gears interface with the side gears. Unlike viscous or clutch plate systems that rely on fluids and inevitably wear out, this operates purely through gear interaction. When one wheel starts slipping, those inclined helical teeth generate axial thrust forces. They slide just slightly in their pockets, creating friction directly against the differential casing itself.
And it's that internal friction that resists the speed difference, smoothly biasing the torque over to the wheel that actually has grip. In this specific Formula Student design, they engineered a very precise torque bias ratio of 2.09 to 1. Pretty impressive. Also, before you ever commit to the massive expense of CNC machining and closed-die forging, you print 3D prototypes. You can see them here. It's an absolutely crucial step to verify tolerances, assembly fitment, and the basic kinematics before cutting any real metal.
Section 6, materials and differential cases. Because honestly, none of that brilliant geometry we just talked about matters if the materials simply yield under massive thermal or kinetic loads. Over the last century, automotive engineers have constantly chased the holy grail, the ultimate strength-to-weight ratio. Back in the 19th century, we started with cast iron. Easy to cast, sure, but brutally heavy. By the Industrial Revolution, we upgraded to high-strength steel alloys to handle intense hypoid gear loads. Fast forward to the mid-20th century, and mass production shifted toward aluminum to shed weight and, critically, dissipate heat. Today, we're living on the bleeding edge with magnesium and advanced composites, maximizing strength while dropping the vehicle's center of gravity as low as geometrically possible.
To put all that into perspective, let's look at the finite element analysis, or FEA, for that custom helical limited slip. The whole secret is balancing your materials perfectly. The team spec'd EN19 steel for the pinion and side gears, yielding a massive 650 megapascals of strength. That practically guarantees extreme fatigue life against shock loading. But then, they paired that heavy-duty steel with a 7075-T6 aluminum casing. The result? Look at those safety factors. A 3.7 on the lightweight casing and an unshakable 11.0 on the side gears. That is what a highly optimized, bulletproof mechanical package looks like.
So, to close out our masterclass, I want to leave you pondering a very real existential engineering question. We are rapidly accelerating into the EV era. We're looking at vehicles utilizing independent, software-controlled hub motors that deliver instant, microsecond torque vectoring on a per-wheel basis. With all that digital precision, are these beautiful, incredibly complex mechanical differentials destined for obsolescence? Is this literally the final chapter for mechanical drivetrain engineering as we know it, or will the raw, undeniable reliability of physical gears always find a place, especially out on the track? Let that simulate in your mind for a bit. Thanks for hanging out on the shop floor with me for this explainer, and keep engineering the future.